Good afternoon, friends. Hi, everyone. Welcome to our webinar today, where we will be talking about how to effectively reduce inputs. And here's the important caveat: reducing inputs while maintaining or increasing yields. One of the narratives around regenerative agriculture for some time has been that it's possible to reduce inputs and to harness soil biology to deliver nutrients and make them available for the growing crop out of the existing soil reserves of everything that has been there historically from a geological profile over however many centuries or millennia, as well as tapping into the products that we have applied in recent decades that the crop plants have not utilized. And while this is an interesting narrative, the common expectation has been that we're going to go through this transition period where we discontinue or reduce the use of inputs, and we're going to get this drop off in yields and crop performance until soil biology starts kicking in. And that need not be the case. In fact, if that is the case, I would suggest it's only as a result of us making uninformed management decisions, because our experience has been that when you manage it well, you can, at the very least, maintain yields, and it's very possible to also increase yields while reducing inputs at the same time. And this is a very important conversation in today's world. The expectation for some time has been that if we try to use or to adopt regenerative agriculture practices or organic agriculture practices and continue the use of inputs, then our input costs are going to go up. And we're going to spend more money per acre than when we were buying nitrogen and phosphorus and potassium fertilizer. And of course, everything is context dependent. Different farms are different. That may have been true for some farms in the past, but it's rapidly becoming less true. In fact, in many cases, it hasn't been true historically. And today, it is not true on most operations as a result of the rapidly increasing input costs. So because of the challenges with input supply and input costs, I think this is a very timely conversation for us to really think about how we can reduce inputs wisely while maintaining and increasing yields. And on our webinar today, we have David Miller. David has been a part of a leader in the Advancing Eco-Agriculture Consulting team for the last decade plus. He's an invaluable member of our team and has observed and experienced a lot of these management transitions on many different farms. So David is going to be giving us a presentation on what he has observed and what he has learned. And if at any point in the conversation or in the presentation you have any questions, feel free to type them into the Q&A box. And then David will respond to those, and I'll be here as well at the end of the presentation. So thank you for being here. I'm sure you're going to find this a really enjoyable conversation. Thank you, David. Turn it over to you.
It's good to be with you again and to talk about regenerative agriculture, which has been what's kept us both going the last 10 years plus. So it's good to be continuing to learn, and I look forward to sharing some thoughts on reducing inputs through regenerative agriculture. This was inspired by a question that came from one of John's earlier webinars on how to reduce inputs, especially fertilizers in sandy soils. And so this presentation and this conversation, which I'm hoping to have a conversation, I'll just give you an outline here of some thoughts on reducing inputs, especially fertilizer inputs, and then we'll look forward to a conversation at the end. So I'm going to start with a question here. If you could reduce your inputs by 35% and maintain yields, would you do it? And now that 35% could be any number there, 50%, or maybe it's 20%, and maintain yields or increase yields, as John said, would you do it? And I don't think I know of anybody who would say that they would not reduce their inputs if they could do so and maintain yields. So let's take a look at those inputs. And I just want to take your thoughts to your operation. Let's just pause for a second and ask ourselves the question, what are the inputs that I am using today? What are the inputs that I used in 2021 to produce the crops that I produced? How much nitrogen was applied? How much phosphorus was applied? What was the timing of those applications? Did the fields where I put on more yield more? Did they yield less? What were the correlations that I saw with what I applied and what the end result was? Are there any applications that you applied that you're not sure if they were effective, or that you only applied because someone said it worked on their farm? Was there a purpose and a reason for each of the applications and for the timing at which you put them out? So in the conversation about reducing inputs, which obviously, and it's been a theme or a thrust and a part of the conversation for organic agriculture and now regenerative agriculture, this also comes up, is it'll allow you to reduce inputs. It will allow you to reduce inputs. And my question following this is, if the inputs that you're using, if those inputs are doing something for your crop, if they are doing something for your soil, if they're doing something to improve profitability, why do we want to reduce them? And thus the heart of this conversation is, let's consider the inputs that we're using. Let's consider the short-term and the long-term value, the long-term and the short-term challenges that can come from whatever those inputs are. And we could talk about insecticide, we could talk about fungicide, we could talk about water, we could talk about, there's a lot of inputs that go into the production of a crop. But today we're specifically going to be talking about inputs on the fertility side, fertilizers, the nutrition part of producing a crop. And with that, I wanted to just take a quick look at the history of agriculture and of the fertilizer. And I found this gem of a book titled Soils and Men. It's the Yearbook of Agriculture from 1938, and it's a bit more comprehensive than most of the yearbooks of agriculture that USDA put together. But on one of the very first pages, I found these paragraphs of a man who had a fine horse. He was very proud of the horse. It was a great horse. And one morning he came to the barn and the horse was stolen. And he was grieving about and just asking himself the question, why had he not spent a couple dollars and put a lock on the barn and saved the horse? And he resolved that he would give better protection to the next horse that he had, but he knew that he would never get one as good as the one he had lost. The United States, this is the second paragraph, has been like that about its soil. Within a comparatively short time, water and wind have flayed the skin off the unprotected earth, causing widespread destruction, and we have been forced to realize that this is the result of decades of neglect. The effort to relieve economic depression for farmers has also forced attention to the soil. In the old Roman Empire, all roads led to Rome. In agriculture, all roads lead back to the soil from which farmers make their livelihood. So as early as 1938, the people putting this book together, which it was written by many different authors, in the preface, it noted that there was more authors and more input from across all of US than any previous agriculture yearbook. So on the history of agriculture, we realize that there's been challenges for a long time. But let's look at the history of fertilizer, and especially from the aspect of what has happened since we've started using fertilizers. So in 1828, Carl Sprengel made his first recommendations and realized that he would get a growth response from ammonium and nitrate as fertilizers. In 1910, the Haber-Bosch method was developed to synthesize ammonia. So people were now, from 1828 to 1910, people really weren't able to, it wasn't commercially available. In 1910, it became available, but there was very little applied commercially until after World War II, when lots of infrastructure was put into place for this manufacturing. And then after the war is when lots of nitrogen fertilizer, especially, and other soluble fertilizers started to be applied in large volumes. As we can see by this one graph, which is from Germany, you can see in 1880 up to 1940, 1950, there was minimal application of commercial fertilizers. And from there, it increased significantly. Looking at another graph, you can see US, India, and China, there was from almost no fertilizers in 1960s to 2010, significant increase in fertilizer applications. Now, on this next slide, we see the grain production per ton of fertilizer in the same time frame. And as we can see, comparing the two, let's just take US. We've doubled the amount of nitrogen that was applied, but we've by no stretch of the imagination doubled the amount of grain that was produced per ton of fertilizer being used. So lots more fertilizer being used, but not really more grain being produced per ton of fertilizer being used. So if our nitrogen input isn't really increasing yields, and there's not been an increase in soil organic matter, which I'm sure you're all aware, and the USDA book Soils and Men clearly indicates that it's been lost. So if increasing the inputs isn't increasing yields and profitability, the answer must be to reduce inputs, right? And that's where we are. How can we reduce inputs? So can we learn anything from what people used to do before we had fertilizer, before we were able to apply fertilizers? 1400s, 15, 16, up to the 1800s, how did people grow crops? And people had rotations, people put on animal manures, there was fish fertilizers depending where people were. So various forms, and it was about the system being cycled. The carbon was being cycled. There was the organic matter, or the carbon in the soil, was not being burned off when there was no crop growing, which we'll touch on later here. Let's not be reducing inputs just for the sake of reducing inputs. If the inputs that we're using are increasing profitability, are providing long-term solutions and long-term viability of our operation, then let's not be reducing those inputs. And the secret to profitability, which is what we all are looking for, and profitability can be in cash, in equity, and that equity can be financially, or it can also be in better soil health, better longevity, better resistance to the various challenges of weather and of water, and all of these things are also a part of profitability. And the key to this is the right inputs at the right time, and the right amount is also very important. So how do we decide what the right inputs are? How do we decide which inputs to reduce, which inputs to keep, which inputs to increase? And here's some thoughts. We need to look at the function of the input, and going back again to your operation in 2021. What are the inputs that went out on your operation? What was the reason you put that input? What is the purpose that it served, and was it effective in serving that purpose? What was the timing of those inputs? And sometimes those timings are dictated by things that are beyond our control, or are very difficult to change and alter because of the production setup that we have. But think about the timing of those inputs, and how did that timing affect the carbon cycle? How did that timing affect the water cycle? How did that timing affect the nutrient cycle? How did that timing affect the symbiotic relationship between the plant and the biology? what are the effects? So whatever input, if you're talking nitrogen, if you're talking phosphorus, if you're talking potassium, what are the effects that that input had in your soil? So let's just take a little bit of time and talk about the effects of synthetic fertilizers. And here's a short list of things to consider. And there's probably a lot more that we could dive into, and we can do this in the Q&A session. So I'm putting this out to stimulate your thoughts, because we could put out a recipe and say, oh, this is it, but it's not that simple. Your operation has its own unique set of challenges, set of advantages. You as an individual have unique insights and experiences that need to be considered in this journey of regenerating your soil, regenerating your operation, the farm, the whole ecosystem. So it's not as easy as just one recipe fits all, but there are principles, and the better each of you can understand the effects that the inputs you are putting out has, the better equipped you will be to make those input decisions and where to reduce and when to reduce and what to reduce. So some of the short-term effects that come from applying water-soluble chemical fertilizers, nitrates, high-salt fertilizers, is you'll get an increase in electrical conductivity. And if you don't have biology, and if you don't have organic matter, then sometimes you can actually get a short-term beneficial response of increasing the electrical conductivity in the soil. But long-term, it will oxidize the soil, and you'll end up with a loss of organic matter. You'll end up with tied up nutrients when you artificially enhance the EC, and the oxidizing effect right along with that, where you have nutrients that are going, especially the metals, manganese, iron, that will be oxidized, will not be available for plant metabolism, will not be available for plant uptake, and also will be much more disease enhancing, because in an oxidized environment, many of the what we call pathogens are able to thrive, whereas in a more reduced environment, they will not be able to thrive. And so you could have the same amount of verticillium or the same amount of charcoal rot or whatever soil-borne pathogen you want to think of. Having an oxidized environment is going to give those the opportunity to be dominant and to actually become a problem. Whereas if you have a reduced environment, then they can and will, in most scenarios, they are there, some of them even as beneficial organisms that will transfer or convert to what we call pathogens, although most of them are actually just cleaning up dead plants that we're trying to keep alive until the end of the season, or keep erect. And then we call them pathogens, but really it's the environment we created by the fertilizers that we put out there. Soluble nutrient tie-up can especially happen whenever you're putting out phosphorus, soluble phosphorus products like monoammonium phosphate, diammonium phosphate, things like 2020, 1034O. These soluble phosphorus fertilizers are manufactured by stripping away and breaking apart the tricalcium phosphate bond, which means your phosphorus is in a simple ion form and has a triple negative charge, which means it will very quickly connect with positively charged elements, and oftentimes that's calcium. So when you put out soluble phosphorus especially, it will tie up where your phosphorus availability will very quickly be reduced or completely be gone in a short amount of time. And in the process, it will reduce the availability by tying up the calcium. So you end up having less phosphorus and less calcium than you did before you actually made the application. Microbial symbiotic relationship disruption can also happen from these putting out lots of nitrogen ahead of the crop where the crop doesn't need nitrogen, and the nitrogen fixing bacteria has really no purpose, no advantage. The plant's not feeding the nitrogen fixers because there's plenty of nitrogen out there. Same thing can happen with phosphorus, and there's quite a bit of research on phosphorus or in the symbiotic relationship of mycorrhizal fungi and the plant being disrupted with too much soluble phosphorus up front. And when we talk about symbiotic relationship, maybe I should just clarify that for a second, is where the plant is feeding the biology, and in exchange, the biology is feeding the plant. And so when the plant doesn't feed the biology, obviously the biology can't thrive. And that's what happens when you have lots of phosphorus and the plant saying, I really don't need more phosphorus. I've got all this phosphorus early, when it first starts growing and is fixing a lot of those symbiotic relationships. But a couple weeks later, after the phosphorus has been tied up and the calcium's tied up, and the plant says, I need phosphorus, the biology that solubilizes the phosphorus doesn't have a symbiotic relationship, and so it takes longer for that to happen, or it may not happen of that symbiotic relationship being restored. Some of the long-term effects to consider when you're putting out soluble fertilizers is the carbon cycle disruption, and this is especially true for nitrogen. So if you're putting out nitrogen to break down crop residue, or if you're putting out nitrogen in the fall, you will be oxidizing that carbon, and there are no plants there to capture the carbon and through photosynthesis convert that carbon dioxide into glucose or into other forms of carbohydrates and put them back down in the soil. So this is where timing is very important, is if you apply the nitrogen at a time when there's no crop to absorb the carbon dioxide flush that comes from that nitrogen application, that means that carbon cycle is now broken and you lose a lot of carbon to carbon dioxide, which means your organic matter is going to decrease. And with that, obviously tillage also will give you significant. So if you're doing a tillage application and then broadcasting your nitrogen, or vice versa, where you're broadcasting your nitrogen and then doing a tillage application, you're compounding those effects. And the long-term effects of it, as we saw with one of those first graphs where the increase of nitrogen, it just continues going up, and the yields per ton of input is not going up at the same level or at the same trajectory. So the more we burn off the carbon, the more we negatively impact the biology, the more compaction we have, the more challenge we have in water infiltration, the more dependent we become on these inputs to provide us with a little bit of an EC effect, to have a chemistry effect on that nutrient release, so that the nutrients which are, you put on soluble phosphorus, or let's say you put on a sulfur product, and you get this chemistry reaction and you get some nutrient availability, but you have to do that constantly. You always have to be applying in order to grow the crop. And then one of the things we see a lot is you put on nitrogen, but then the crop runs out anyway. So the other thing that I want to look at is, and help to just get your thoughts spinning on, is the soil itself. As we read there, all roads lead back to the soil. And I think that's very true. Everything we do needs to be going back to the soil. And one of the things with inputs that has long been touted is we need to put it out there. We need to build that soil. And there are cases where that's true. But I'm going to show you a soil sample, and this is a total mineral extraction of a very sandy soil. I've got calcium highlighted here at 1,873 parts per million. Now this is the same soil, and it's an ammonium acetate extraction. So this is showing what is a bit more available, but is not in water solution or is not plant available necessarily. And you can see that on calcium, we have 939 parts per million. And now this is a saturated paste analysis where we use deionized water, or the lab did, and extract it, measured the calcium, and there's only 19 parts per million available. So you have 1,800 parts per million in the soil. You have 900 within the reserves, and you have only 19 parts per million that are plant available or in the soil solution. Looking at manganese, you have 23, which is actually quite a low number for the total soil report. And then you bring in the regular soil sample, or the ammonium acetate, which this is a DTPA extraction on the manganese, and you have 3 parts per million. So you have 23, and then you have 3, and then on the plant available, you have 0.02. So it's non-detect. It's less than 0.02, which is the minimum amount that they can detect. So the question here is, should we be decreasing, reducing inputs here? What inputs do we need? What inputs do we need to increase? And then one of the more common inputs is potassium. So on this particular sample in a sandy soil, you can see that we had 86 parts per million of potassium on the total mineral extraction. They take all the potassium out. And on the regular soil sample, we have 81. So that means that the majority of the potassium that's out there is fairly available. It's showing up on the ammonium acetate extraction. And then you have 17 parts per million on the available extraction. What's the point of this? What is the importance and significance of this? This is a sandy soil. When you look at soils that are, and I'm thinking of a sample that I did way back, probably the second or third year that I was doing consulting work. I got this soil analysis from a grower in Nebraska, and he was showing that he had 8 pounds per acre of phosphorus, and a biological consulting company had recommended that he put out 1,000 pounds of rock phosphate. Now, I had learned a hard lesson earlier that putting out a ton of rock phosphate doesn't necessarily increase your phosphorus numbers. So I suggested that he do a total mineral extraction like you are seeing here. And on that report, instead of having 8 pounds per acre, he had 2,500 pounds per acre of phosphorus. So there was lots of phosphorus in the soil, but it wasn't showing up on his soil analysis, just his regular soil analysis. So if you looked at that, just the regular soil analysis, you would say, well, you really need to be adding phosphorus. And one of the inputs would have been phosphorus. But had he put out phosphorus in that scenario, I don't believe his phosphorus numbers would have come up one bit, because the reason he didn't have phosphorus available is because he did not have an environment for the phosphorus that was in the soil to be metabolized and to be in a stable form by biology. And so unless he changed that, unless he created a less oxidized environment and an environment with higher organic matter, with more biology, he wasn't going to realize any amount of phosphorus that he put out. He could have probably put out a couple ton and maybe moved his numbers up just a small amount for what was soluble within those applications. But if you can follow the point, putting out MAP, putting out DAP because you are low in a soil sample does not equate to having more phosphorus in your soil, and you probably have plenty of whatever nutrient you want to name out in the soil. Now, I will say on this particular sample that we have on the screen here, you can see that there's a very narrow margin between the total mineral potassium, or this 86 part per million, compared to the 81 part per million of potassium. So that's telling me there's very little within the soil reserves, and that would be one area where putting out potassium would make sense. That's an area where it doesn't make any sense to reduce inputs. So back to our book, and back to the quote, in agriculture, all roads lead back to the soil, which is why the regenerative soil primer has been such a powerful tool in our toolbox. And I don't know if John knows. Yeah, he probably does. I shouldn't question you on that, John. The wisdom of this program, when you put this together, and the effectiveness of this has just been amazing. And I want you to notice this name, soil primer. What does primer mean? It means it's primary. It is the main thing. It is the key thing. When we put on a foliar application, and I just want to run you through this real quick. If you put a foliar application to enhance photosynthesis, and you have a sap analysis so that you're putting out the right nutrients, but you fail to put on or to address the primary thing in the soil, the primary area, then that foliar may increase your photosynthesis. It may enhance the level of photosynthesis. It may enhance the amount of carbohydrates that are pushed down through the roots. But if there's no biology to receive that and to make more nutrients available from the soil up to the plant, then that cascade has been stopped. And so that's as much as you got out of that foliar. Now, if the primary thing, or the biology, the microbes are in place, then you will have a flush of nutrients become available because there's more sugars being produced because of the application, the foliar application that you made to enhance photosynthesis. And then the plant will become even healthier, which means more photosynthesis, greater capacity to produce more carbohydrates to feed more biology. And that's why we call it the regenerative soil primer. It's because it is the primary part. Without it, you just won't get very far. You can do sap analysis, you can affect a crop, but to really affect the whole system and to spark that regenerative cycle, you really need to make sure you have bacteria, to make sure you have fungi, to make sure you have an environment where all of that can thrive and grow. I found this data to be very striking and very fitting for this conversation. This is a grower in Iowa that took soil analysis, GPS gridded soil analysis. And so what you're looking at here is just a couple of the nutrients, and all of them show similar trends. You look at your total phosphorus, and the H3A is the Haney analysis. So there was a Haney analysis in 2020 before the treatment. Excuse me. And then there was a soil primer, and there was a starter fertilizer application, which I think also included some biology. And what you can see is from 2020, and this was like 6 fields across the farm that I just averaged together. So some of the fields were a lot more than this. Some of them weren't quite as much as this. So this is an average of 6 different fields that were sampled at the same GPS location before the treatment in 2020 and after the treatment at the same time of the year in 2021. What I think is very important to take away from this is he did not apply phosphorus. He did not apply potassium. I take that back. On a couple of the fields, I think 2 of the fields he put on 33 pounds of potassium sulfate of K2O, which means he got a couple pounds of potassium from that. But here we're showing a 72% increase, 36, and this is in parts per million. So 36 parts per million of available potassium to 132 parts per million of available potassium. And to the point I was making earlier about the phosphorus, you could have applied phosphorus. If there's no biology there to make it available, it probably won't show up. You can apply MAP, you can apply DAP at very high rates, but if they get complex in the soil, they won't show up on these tests. There was the minimal amount of potassium, no calcium, and no phosphorus, and you can see how we increase these numbers. Now let's take a look here. I put the results for just the regular soil analysis, so like the ammonium acetate extraction. And actually the total nitrogen, we could have put that in either or category because nitrogen is a very soluble nutrient, if you will, or it's very available in almost any form in the soil. So the total nitrogen before the treatment was 13, and after the treatment was 46. The phosphorus, and this is where I want to draw your attention. So phosphorus, potassium, calcium before the treatment. Let's start at potassium. We had 169 parts per million, and after the treatment, we only had 178. Same field, same averages. You have 36 and 132. So what's out there in the soil didn't necessarily change. A little bit, tiny amount. Same with calcium, from 2,900 to 3,000. So 100 parts per million. But in the available, we didn't quite double. You find this interesting? I do, because what was applied was simply a microbial inoculant, a very sophisticated microbial food and support package called Rejuvenate, and another microbial food source and a very complex food source called Sea Shield, which is shrimp, salmon, and crab. And the combination of those three had such an effect on the nutrient availability. Again, it's not so much about reducing inputs as it is putting on the inputs that will give you long-term beneficial results. Here's just a quick slide on some of the other things we've seen by addressing biology, by making sure our soils have biological communities and a good microbiome working. We've seen compaction reduced in 1 year very significantly, and that's a very consistent. This is not a new product, new program, new material. And I've, of all the products we have, Photomag, Accelerate, list any of them, I've not seen anything that has consistently given results like the Rejuvenate and Spectrum combination or whatever microbial product that you're putting with that. So if you're looking at crop residue digestion, if you're looking at compaction, if you're looking at nutrient availability, this is one of the things that when you look at, well, can I reduce MAP? Can I reduce phosphorus? Can I reduce potassium? Like, can I reduce that cost? The answer is yes, probably. You need to look at your whole operation. You need to look at the whole picture. But when you look at this slide, putting out potassium, putting out nitrogen, putting out phosphorus isn't necessarily going to give you calcium increase, is it? And this isn't, we weren't able to show everything, but manganese was very similar. Iron was very similar. Let me see, the magnesium was very similar. So it's just all of the nutrients, and we didn't apply those. It was because we're applying something that is going to have a greater impact than just this one function. There's many things that are going to come by applying a primary part of the system, by making sure that the primary part of soil regeneration of the whole soil plant symbiotic relationship is in place. We don't have biology, everything stops there. So wherever you are, you may be way down the journey of regenerating soil. You may be sitting here and for the first time thinking about, how can I reduce fertility? I just want to encourage you that sometimes reducing isn't the key to more profitability. Sometimes it is just changing what we're applying to have the greatest long and short-term benefit. This is just to stimulate your thoughts, and we'll open it up for Q&A. John's here, I'm here, and we'll just fire away.
David, one of the questions that I have for you, you have talked a little bit about the science and some of the things that you've observed. And you've talked about some of the considerations about whether we should consider reducing and when we should consider reducing pesticide applications. But I'm curious about your experiences from a very practical perspective. How much have you observed farmers reducing their fertilizers generally? And I know it's a very broad question and every farm is unique, but what have you observed as a general trend of reduction as a reduction of fertilizer applications on the operations that you've worked on?
So as I think of growers that I've consulted with in the past 10 years and growers that I'm actively consulting with now, it's very common to reduce nitrogen, like soluble nitrogen inputs, in the first year by 20 to 30%, just simply by using the humicarb, molybdenum, and that nitrogen stabilization recipe that you put together. Very common to do that and not lose out on yields. Now, longer term, I have growers who are continuing to reduce to the point of being at 20% of what they used to be. And so I would say, John, very easily a 30 to 50% reduction within the first 3 years is just like a very common trend.
And that's true for nitrogen. What have you observed with phosphorus and potassium?
Well, actually, phosphorus and potassium are even easier. There's a range all over the board with all the different crops, but I have a cotton grower that didn't put on any potassium, and there's been plenty of potassium. And I will say that in that experience, this was actually 2 years ago when he was first, looking at the soil primer and the biology and all of that, and where he had put out the biology a year in advance or in the fall and then planted cotton in the spring, there was no need for potassium based on the sap analysis as compared to where he had only put out some biology in furrow. We still had to put some potassium on. I believe that was for the cotton. We've seen similar things in the onions, but phosphorus, most places, if you get the biology going, phosphorus can very quickly be reduced, which is very exciting. And when you look at what phosphorus prices are doing right now, and you look at spending the same amount of dollars on a microbial inoculation, and then you look at the phosphorus availability and the plant response, I have very little concerns about lowering phosphorus and potassium very early out of the gate.
Yep. David, you can drop your screen share. And just to follow up on your comments, I think our general recommendation would be to, again, it's a case where you don't have to guess. You don't have to fly into this blind. We now have access to this soil analysis, which where we can measure the reserve of nutrients. And there are exceptions, like really sandy soils, for example. But for many soils with different geological basis, you will find that they have phosphorus levels and potassium levels far beyond what you will remove in decades, or in some cases even centuries of crop removal.
Right.
So there's one of the questions that has come through. Where did it go here? It's a question for you, David. Your data references, you included some of the Haney analysis, the H3A analysis. Is this a soil testing method that you would consider reliable? Or at the very least, is it less susceptible to the shortcomings you acknowledge with other soil testing protocols?
Great question. And whether it's Haney analysis, whether it's the new microbial analysis, whether it's whatever analysis that you want to look at, SAP analysis, they all have to be tools. And the more tools that we have, the better they complement each other. So I don't see this so much as a standalone, this is the only soil analysis you need, as yes, I would consider it a reliable tool to complement the rest of the soil analysis to help us understand what fraction of the soil is in what spectrum of availability. And so it's a good tool to measure the nutrients that are available, but also how effective and how well your biological community is doing in your soil.
There's a few more questions here for you, David. One of them is soil primer consists of spectrum, rejuvenate, and sea shield. I think these are microbes, mostly bacteria and foods. Is the idea to foster a bloom of bacteria, thereby stimulating populations of other microbe types in the soil food web, such as fungi, protists, nematodes, etc.?
Yes. Yes, these packages, microbial packages, the spectrum, the biogenesis, whichever of the microbial packages that we add to our soil primer programs were developed by Bruce Tainio. And as I understand it, they are the foundational species and strains that are then able to, from that, the plants will be determining what biology that flows from that. And yes, definitely on the fungi and the other types of microbes, the bacteria is the lowest on the food web. So get a bunch of bacteria and you'll probably have a bunch of the others.
There's an interesting question here, David, on the use of liquid manure from Brad. How does the addition of liquid dairy manure affect nutrient availability in general and how it works in your program?
So dairy manure is not always dairy manure, as some dairy manure is. Not all alike. So I have seen dairy manure that was well agitated. There was microbial inoculation. It was actually kind of a digestate. And I've seen dairy manure that was very, very harsh, biologically speaking. I've seen applications of dairy manure that, completely, I shouldn't say completely destroyed, but it certainly wasn't good on the earthworm population. And so that if you are doing that, there's lots of other things that are suffering. So my answer to that, John, would simply be that if you have the resource of dairy manure, you are cycling, as we have seen that, cycling nutrients is a good thing. But the concentration of that and the solubility of that can sometimes be a challenge. So how does that fit into our program? If it is like a lot of dairy manures are, we would recommend that you add a carbon source to help stabilize the ammonia. We would recommend that you inoculate with some microbial inoculant to help digest and to stabilize those soluble nutrients so that when you're putting it out, and even better, if you have carbon and you're able to complex it with carbon and do a slight compost, now you're even further ahead and have a lot less negative repercussions on biology. And like I mentioned earlier in the presentation, whatever resource you have, wherever you are, think about what is the effect on biology, what is the effect on nutrients, what is the timing of it, which is something else to consider. When are you applying this? At what rates are you applying it? Because applying 2,000 gallons of liquid dairy manure is going to have a very different effect than applying 20,000 gallons of liquid dairy manure.
Yeah, I think, when we talk about liquid manure, I always find it interesting that we have this material which has the capacity, it has the potential to be so exceptionally beneficial and to be so useful for soil health and for soil biology. And in so many cases, because of the way that it's been mismanaged, it is actually toxic and has a negative effect on soil biology. And you mentioned killing earthworms, and it also kills lots of other things. I've had this interesting conversation several times where people ask me why they have velvet leaf growing in their fields, and or why they have this or that weed pressure. And for a number of weeds like velvet leaf in particular, you can just simply point to the liquid manure applications and say, well, you're putting on liquid manure, then you're putting in wash house or milk house wash water, wastewater with all the soaps and the bactericides and everything else. And it's really simple when you stop to think about it. A liquid manure pit can actually smell good. It can be the equivalent of a compost tea brew, or it can be toxic and stinky and smelly. And it's really a question of our management. So it's possible to have liquid manure that is really healthy and has a tremendous positive effect, or that it has a negative effect. And it's determined by the management decisions that we make as farmers and as farm managers. There is a question here from Danny. Are you able to see the nutrient availability in standard plant tissue tests or only through sap analysis?
So nutrient availability, when we talk about nutrient availability from a soils perspective, your well, I guess you can see what's available in the soil by either tissue or sap analysis. But if you are measuring with a sap analysis or with a tissue analysis, you're going to be seeing what your plant took up, but it's not going to give you any indication of what you should be applying or what your plant is not getting at this time. And so a tissue sample versus a sap analysis to evaluate whether your plants are getting the nutrients they need and where your deficiencies are as far as from a soil nutrient availability. The sap analysis is going to give you actionable data that you can look at and say, oh, we need this. And we can typically see 2 to 3 weeks ahead of when you are going to have visual symptoms when we look at a tissue analysis, where on the sap analysis, whereas on the tissue analysis, you're measuring all of the structural minerals like your calcium, like your boron, your iron in the chlorophyll, etc. So it's not measuring where your plant is today. It's kind of like trying to determine what nutrition you need by measuring the calcium based from an analysis of your structural components. Like if you analyzed your hand, you probably get a response that you have plenty of calcium, but in reality, you might need calcium in your diet. So you can look at both of them, or either or can give you some information, but the sap analysis is by far going to give you the most actionable information that you can respond to in this season.
Yeah, I think David's trying to be diplomatically correct here in the way that he answers the question. We've obviously taken a position as a company that we're very strong in favor of sap analysis. And I think the way that we would express it is quite simple. We are not willing to give consulting recommendations based on dry matter tissue analysis only because they are too unreliable. And that's kind of where we stand. So there's a question here from Peter. I have applied the AEA soil primer on wheat stubble this fall, and I'm planning on using the planter application next spring. Do I apply the soil primer again on the corn stalks next fall and the following years? The rotation is corn, soybeans, navy beans, and winter wheat. So I think that the question, in essence, if I'm understanding it correctly, is do I need repeat applications year after year and into the future? And how long into the future does that need to extend?
Mm-hmm. There are as many answers to that as there's farms and growers on this call. Peter, to answer your question, I would just simply say that when you make an application and you see the response, and then it really depends on what you are doing between those years. If you're destroying that biology, if you're putting out chemicals that are going to destroy that biology, then yes, you will need to continue. Every time you do things that disrupt that biological symbiotic relationship with the plants or the environment where the biology is going to be cut back, then an application makes sense. So there may be a time within your rotation, and as you look at all of that, and this is where the AEA consultants are trained to look and say, okay, well, how can we help you make the most money? It's not about just putting out 2 gallons of rejuvenate every year and you just have that blanket. It's like, okay, well, if I were you, I would apply it in furrow when I'm planting your beans, because you get the best inoculation across the whole acre immediately. So that makes sense. But then you have the crop residue, and maybe you have challenges with a corn disease. And so you want that residue to be broken down as quickly as possible. So that's when you want to be applying it in the fall, which there's lots of advantages for that nutrient cycle, and especially the carbon cycle, to be happening in cold temperatures, which is why we have been such strong proponents of applying the soil primer in fall, is the advantage we get from a longer chain, more stable carbon when you have that digestion in the fall. So inoculating in the fall will give you more biology and more of that decomposition during the winter time. So, we're talking about reducing inputs. And I want to go back to the key point. Let's not reduce an input that's making us money. Let's look at what inputs are giving us the return on investment. And let's continue applying those inputs. And when those inputs are no longer a key, then let's reduce those. It's never lime was important this year, so lime must be important for the next 5 years. No, it's you put on an application for a specific purpose at a specific time for a specific reason. And when you put on the soil primer and then you have that soil built back up, and you really don't need the primer or the biological inoculation may not be needed, or maybe you reduce it. And the key thing is measuring. What's working? Why am I doing this?
Hey, David, that was a great answer and a great conclusion. Yeah, the key piece is measuring and knowing whether something is being effective and producing a response or not. And the reality is that if farmers actually did that across the country, there would be just a fraction of the fertilizers being applied today than what are being applied, because our experience and observation with sap analysis has been that in many cases, the products that are being applied are being wasted. Plants are not absorbing them, they're not utilizing them, and there's a lot that is just staying around in the soil profile or going down the river. I want to be respectful of everyone's time. There's quite a few questions that have come through, and we're not going to be able to answer all of them. So we're going to take time for one more, and then we're going to wrap this up, and we may need to respond to some of you after the webinar is over. So there's a question here from Mary Ellen. I'm thinking about managing corn next year without chemicals. I was considering applying composted turkey litter this fall. Would the regenerative soil primer be complementary to this?
Yes.
And David, what David is thinking without saying is, he's thinking, do you need the turkey litter? Do you need the soil primer? Maybe you still do need some fertilizers. Again, you need to measure, and then we live in a world today where there is no excuse for guessing. We don't need to guess anymore.
That's right. I'd like to just maybe expound on that for just a second, John, on how that when you combine, say, a manure like the turkey litter here, when you put the soil primer or the biology on that, it provides you with additional carbon sources to complement the rejuvenate and the sea shield that's already there. So you actually have an even greater amount of food source and soluble carbon. And so you can actually grow that population even more. So it's a perfect time to spread your turkey litter and put a little bit of biology on. But you make a great point. Do we need turkey litter? And I will maybe a bit biasedly say you need soil primer. If you're not putting that on your soil, there's really no question about that.
Yeah. All right. Well, David, thank you very much for being here, for sharing your experience and knowledge that you've learned working with growers over the years. I really appreciate you being here and being on the AEA team. Thanks everyone for joining us here in this webinar. I hope you found it useful and valuable. And if we didn't get to your questions, please feel free to send us an email, and our team would be happy to connect with you or to talk with you on the phone. Have a wonderful day. Thanks everyone. Be well.